My name is Steve Lindholm, Consulting Engineer at EDT, and I appreciate everyone here for joining this installation of Tech Talk. Today I will be presenting the fundamentals of finite element analysis and how computational modeling can evaluate structures, components, equipments, and systems. This Tech Talk will last 15 minutes and is being recorded. A copy of the recording will be shared afterwards. If you have any questions during the session, please use the chat feature to post them. I will answer as many questions as I can at the end of the remaining time at the end, or you can reach out later if you think of something afterwards. That's the framework of this Tech Talk, so let's get technical. As a short introduction to your presenter, I am a consulting engineer licensed in multiple states as a naval architect, marine, and mechanical engineer. I hold dual licensure as a mechanical engineer and a naval arch in those states which recognize these disciplines separately. I graduated from the University of California with a bachelor's in 1983 and have been active in industry ever since. I have three objectives in this presentation. One, to explain the basis of finite element analysis, or FEA, how the concept of FEA was developed and the type of analyses available. Two, to present the benefits of FEA for evaluation and development of products. And three, the ways FEA results can be presented. The basis of FEA is the breaking down of a large problem into smaller parts, which are referred to as finite elements, applying the equations which explain the conditions acting on each element, and linking the elements with common dependencies. Computational FEA now allows an engineer or a scientist to solve very large systems of equations with many dependencies. These large dependent systems of equations would not have been feasibly possible to solve manually. Truss structures, such as a bridge, for example, can be thought of as a simple FEA problem. Those of you who have taken structural design courses have solved these problems before. And yes, if there's any civil engineers out there, you know what I mean. Trusses consist of beam elements connected at nodes. These nodes create common dependencies between the beam elements and the equation of state, or the beam formulae. This is a classic model of a simple truss. Not the simplest, though. It consists of beam elements, numbered through 1 and 9 in this case, connected by fixed nodes. The truss has a distributed load, W, along the bottom, let's say like a roadway, with reactions at each end where the truss is supported. To analyze the truss, we explode the beam elements and determine the dependent equations. The only beam elements which have external conditions are elements 1 and 2, which are the roadway. On all the other beams interacted by their dependencies. To solve the equations, elements 1 and 2 are modeled as beams, with one fixed end and one simply supported end, where the reactions are. The common node between the elements 1 and 2 and elements 4, 5, and 6, as you'll see, is the fixed end. For each node, the forces are broken into their vertical and horizontal components. Written here are the beam formulae to solve the vertical force for one simple and one fixed support. The vertical forces for the other beams must sum to 0 for the internal reactions to balance. To solve the horizontal forces in each node, the sum of the moments at the common node of elements 1 and 2 must equal the moment at the fixed end. Change there and I don't see it. The solution to the truss problem is a system of equations. Each equation is solved for one unknown, and the result is inserted into the other equations until the number of equations matches the number of unknowns. For a computer, this would be trivial. When a system of equations becomes complex, computational FEA can be left with too many variables and not enough equations. What computational FEA does in this case is to use iterations of solutions. guesses, if you will, until the error of the equation solutions converges on a vanishingly small number. Applications of FEA. In theory, FEA could be used to model anything which can be described in 2 or 3-dimensional model, has inputs which are defined by a mathematical equation, has element properties which can be defined, and has defined constraints. If the properties or constraints cannot be fully defined for the model, then the FEA will fail. Common engineering problems which lend themselves to FEA: solid mechanics, the stress and strain, which is probably the most common use of FEA. Heat transfer, modeling how the heat goes in and out of an object. Fluid dynamics, which is the flow and pressure. Again, you might find that in something like analysis of a ship hull resistance, things of that nature. Pipes. Electromagnetism can be modeled. Acoustics can be modeled. And we can do multi-physics combinations of the above. For instance, as in the picture there, the impeller shaft stresses in a cryogenic pump. So it's modeling the flow. From the flow, you get the forces. From the forces, you can then get the stresses. So types, EDT uses computational FEA software capable of working with both linear and nonlinear behavior. Linear behavior is like a spring. If you pull or push it, it deflects. Release it, and it returns to its original shape. Nonlinear behavior is a superset of alternative behaviors such as creep, permanent stretch, and other phenomena, of which linear behavior is a special case. I have listed here a number of various analyses EDT can carry out. For instance, steady-state static loads, hyperelasticity, such as very stretchy materials, time-dependent analyses, modeling the stresses of interference fit as the parts equalize in temperature, force vibration problems, resonance, and others. This list is not exhaustive. FEA can do much more and in almost any combination. All you have to do is ask us. What we need out of FEA is answers. This is a partial list of the solutions, part answers, the software provides to the problems involving stress, displacement, vibrations, or heat transfer. The reason you use an expert with FEA capability is the expert's ability to interpret the solutions of the equations and models into an answer which can be acted on. EDT takes these solutions and the outputs from a program to inform our commands. Output from the program gives output the program gives directly include tabular data, intensity gradients, display shape, and animations. So some of the benefits of FEA for those in evaluation and development: we can do failure analysis, the causation of a problem, failure mechanics, and the failure mechanism. We could do predictive failure, where we're looking ahead at what could happen should a certain type of load be put on, or over time, the type of failures you may get from time-dependent over time problems. Vibration analysis, resonant frequencies, harmonics, and noise. These are all things which we find in machinery and in buildings, which we can model. We can do parametric studies where we can look at more than one potential solution or different load cases, maybe a monotonically increasing load on something. We can do the animations through those parametric studies. We can validate. We can validate the load capacity. We can validate harmonics, and we can validate fatigue life. In legal cases, we can use FEA to validate a case, show the causation, the failure mechanism. We could look at the case viability, alternate hypothesis possibly, maybe the lack of validation. Sometimes FEA could be used as much to tell a attorney or a counsel that, hey, you can't go through with this case. It's really not what you thought was there is not really there. We could also use it to contradict another hypothesis. For coming up with our hypothesis, we can show that this is an alternative and may be another thing to consider. We can provide courtroom visuals, visual aids such as diagrams, the images of how the stress is distributed, and we can bring in animations. Those can be very powerful. They can show what is going on, especially in a time-dependent situation. So when presenting the results of FEA, we can present it in different ways, depending on the needs of the client. We could have a report with the data. Oftentimes you need a report anyway, but it would be a more formal report showing just the information that came out of the FEA program. We can show you visual representatives of stress and deflection. That's basically a picture, right? And animations. Again, animations can be very, very informative to the personnel. The following slides illustrate some of these presentation methods. The following methods, okay, in particular, so I'm going to kind of deviate from my notes here. The project that I'm going to present, it was a motion isolation assembly. As you can see, it looks like 2 plates with a spring system between them. In this case, there was a load that both acted down and on the side of the spindle in the middle of this plate. So when breaking this down, we can give a data report. And here you can see everything. The data is provided in a tabular form. We have the model illustrated. We have the loads illustrated. This is your formal data report. Visual presentations can be used for an overall impression of the relative areas where stress, displacement, motion may be the highest and provides a display of the relative magnitudes. We can grasp these kind of trends more quickly with this type of a display because we are visual animals, and seeing different colors and where things are highlighted can be very informative. Animation takes the visual clues a step further. Animation is especially useful for periodic or harmonic loading situations, where the stresses, strains, velocities, or accelerations can be overlaid on the deflected shape. If you want more information, please email, whoops, hold on, I was going to take a look. Do we have any questions? I don't see any quite yet. Remember, you can leave questions in the chat box. Is it oh, here we have one. Thank you, Geronsko. Excuse me, I probably mispronounced that. Geronsko. Is it possible to share examples of this FEA? You saw some of it. I presented what I can. That kind of leads into something I was hoping we could talk about, because if you do like this presentation and would like to see more in-depth dive into how an FEA simulation is created, EDT is considering a follow-up on this fundamentals. Please provide your feedback to show any interest in another presentation. Any other questions? If not, we're coming close to the end, so I am going to already give you kind of a conclusion here. If you want more information, you can, of course, email or call at the contact information on this slide. We're happy to help. Remember, this session was recorded and we'll send a copy after this closes. Thanks for joining and have a great day.